In this video, I'll explain how to make the Epi-illuminator modules. These allow specialist modes of microscopy, such as Epi-fluorescence, and reflected light microscopy, such as that used for metallurgical analysis. There are many specific forms of Epi-illumination in microscopy. One way to divide them into two broad categories is 1. External beam Epi-illumination, where the illuminating light does not pass down the objective, and 2. Coaxial Epi-illumination, where the illuminating light does pass down the objective. External beam Epi-illumination is easy to achieve by shining a lamp to one side of the objective and needs no special optics. However, this is difficult for higher magnification objectives due to the limited working distance space for the light to get on the sample, and this also restricts the angle of illumination. This type of Epi-illumination will not be discussed further. Coaxial Epi-illumination, where the illuminating beam passes down the objective, is the most common type used in professional microscopes, but requires special optics, which usually, but not always, involves a beam splitter. The PUMA Advanced Filter Block module was described in detail in a separate video, and its integrated plate beam splitter is what enables PUMA to perform Epi-illumination when the LED illuminator and lower collector are connected to its Epi-illumination port. However, there is an important optional upgrade required to the Advanced Filter Block to improve its performance in reflected light microscopy. This upgrade is simple to do. It only requires replacing the detachable augmented reality projector port cover with a modified version of that cover, which includes light blocking extensions, which I call the Epi-stop. The Epi-stop is designed to block these bright reflections of the incoming light, which reflect up the ocular tube from the free edges of the beam splitter. Left unchecked, these cause an annoying strong mist to cover the image when your eye moves even slightly to various off-axis angles when looking down the eyepiece. The Epi-stop cover is a simple direct replacement to the ordinary augmented reality projector port cover. Just remove the two screws holding it in place and replace it with the Epi-stop version as shown. Retighten the screws, taking care not to damage the threads. And that's it. Upgrade complete. You can see how this greatly reduces the reflections and solves the issue. This upgrade is essential for reflected light microscopy, but is optional for fluorescence, because with the latter we use an excitation light blocking filter above the beam splitter. However, even in fluorescence it may reduce some background light if your blocking filter is not 100% efficient. Now I'll describe the two types of illumination collector lens systems that may be used with PUMA in Epi-illumination modes. The first is the standard 2x23mm lower collector alone, which must be used with the 5mm spacer. This collector system gives the most even illumination at low magnifications, such as with the x4 objective, and is the only type of collector system that can be used for fluorescence, because we need the 5mm spacer to house the excitation pass filter. The second collector arrangement uses the 2x23mm collector again, but this time it is held right up against the LED without the 5mm spacer, and also uses the LPC with its integrated front lens that was described in the video on Köhler illumination. This configuration gives the most even illuminated field for objectives of x10 magnification and above. In both collector arrangements, it is important not to use a textured diffuser or other patterned filter, because these illuminators provide partially critical Nelsonian illumination, and any texture or surface marks on any filter will be projected onto the surface of your sample and be visible in the final image. Whatever collector arrangement is used, in this type of coaxial epi-illumination, the objective itself acts as a condenser, and because we illuminate the full back focal plane aperture of the objective with the LED illuminator, we will automatically be using the full numerical aperture of that objective, even up to the high numerical apertures of oil immersion objectives, so as to use the full resolving power of even the highest magnification objectives. The connection of the lamp and lower collector to the epi-illumination port can be made by one of two connector modules. The first is a plain connector with no intervening optics, and this is the preferred method for epi-fluorescence microscopy, because the lack of intervening optics allows the maximum amount of excitation light through to the specimen. The alternative connector module is the polarizing connector, which includes a rotatable polarizing filter to allow epipolarization microscopy. This is especially useful not just to analyze birefringence, but also to reduce unwanted reflections and improve contrast in reflected light microscopy, such as metallurgical analysis. Regardless of which connector is used, it was shown in the video on beam splitters that about 50% of the light from the epi-illumination port gets wasted at the 50-50 beam splitter, the wasted light passing through to the augmented reality projector port, and this large amount of wasted light can reflect back up to the ocular to contaminate the image and reduce contrast. Therefore, if you are not using the augmented reality projector, it is very important to use an epi-black body light sink on the augmented reality projector port when doing epi-illumination to minimize back reflections. When epi-illuminating a transparent specimen, such as with epi-fluorescence, it is also desirable to minimize any back reflections from the illuminating light that passes through the specimen. For that reason, a special light sink epi-condenser was designed. This is only called a condenser because it fits into the same position as the true Abbe condenser and uses the same centration adjustment mechanism, but it does not contain any lenses. To use it, you first choose a cover aperture that is just wider than the illuminating beam coming out of the objective. You then turn on the illuminator and center the epi-condenser until the light coming out of the objective is swallowed up by the black hole of the aperture. The epi-condenser is now correctly set up for use with that objective. These light sink modules, which I also call black holes because of their function, give some benefit just as they are. However, their effect can be improved if their internal surface is coated with matte black paint or flocking that is darker and more matte than the plastic used to print them. This is especially important if you use a more shiny variant of black 3D printer filament, as shown in this comparison. For flocking, I use Optarch Event Horizon flocking paint. This is formulated with a high density of carbon and polymer pigments of various sizes to scatter and absorb not only visible light, but also infrared. This is a microscope image of a thin cross-section of some glossy white inkjet paper painted with Event Horizon to show the range of size of pigment granules that scatter light in all directions. Here is a similar preparation coated with a well-known brand of matte black blackboard paint. Notice the lower density and more uniform size of the pigment granules in the blackboard paint compared to Event Horizon. This goes some way to explaining the superior light absorbing and scattering properties of Event Horizon. Here I show a comparison of Event Horizon, a brand of matte black blackboard paint popular with some photographers and amateur astronomers, and a black fabric. The paints are painted onto brilliant white glossy inkjet paper, which is curled up into a partial tube so as to study the effects of oblique illumination and concavity reflections. I also coat some shiny black PLA plastic with these paints. You can see in this comparison that Event Horizon shows less reflection on the concavity of the partial tubes compared to the blackboard paint. Also, note the superior matte black effect of Event Horizon for very oblique illumination, something that is important for use in optical tubes, although PUMA does not use paint or flocking in its optical tube because the light baffles in the tube prevent internal reflections by design. Now we switch from visible to infrared illumination, where the extra matte black effects of Event Horizon are again obvious. Here you can also see that the black matte fabric becomes useless, because the dye used is highly reflective for infrared light, as opposed to the pigments in the paints. Guarding against stray infrared is especially important when doing image recording with CCD or CMOS camera chips. Here is a comparison of the field of view down the microscope using various light sinks or none at all, with and without the anti-reflective Event Horizon coating. The tests all use white light epi-illumination without a sample on the stage. A perfect system would show a completely black field of view. For these comparisons, I've used the same camera with the same manual settings for gain, shutter speed, exposure, etc. The illumination intensity is also constant between tests. Note that using even uncoated light sinks gives better results than using no light sinks at all. However, the best results, that is, the darkest fields, are gained when the coated epi-black body and epi-condenser are used. The worst results are obtained when the normal Abbe condenser and standard protector cap are used instead of light sinks. Therefore, the use of light sinks is definitely worth the effort to get the best contrast, and especially if you need to look for weak signals such as faint fluorescence. Before showing you how to build the Epi-illumination modules, I'll demonstrate two practical Epi-illumination configurations of PUMA and show you some example images. These images are taken with low-cost CMOS cameras using two methods. The first is an example of the so-called afocal photography or afocal eyepiece projection. This takes the image that comes from the eyepiece and projects it through a complex wide-angle lens assembly of a camera onto that camera's sensor chip. This has the advantage of showing you the whole eyepiece field of view to give you a sense of what you'll see when looking down the scope by eye. The disadvantage of this method is that the image signal is attenuated due to all the glass it has to pass through, and there will be some distortions in illumination and focal planarity due to the accumulation of aberrations caused by all these lens elements. So please bear in mind that the actual image you see down the scope by eye will be significantly better than what is shown with this camera system. The second method uses a modified ocular tube that allows a C-mount camera to be attached in such a way that the primary real image from the objective is projected and focused directly on the chip of a C-mount camera, without any intervening lenses, not even an eyepiece. This has the advantage of greatest sensitivity and reduced aberrations for detailed imaging. The disadvantage is that the image will be greatly magnified, so you will lose a lot of the peripheral field of view. Both cameras used in these experiments are inexpensive generic cameras that give a compressed image stream And furthermore, I will be reducing the resolution to fit this 1080p video frame, and compressing it again for video render before YouTube compresses it a third time. So, the pictures you will see are only a poor reflection of the true quality of the optical image of the scope. Nevertheless, they serve to give you a reasonable idea of what you can expect to see. Before showing you how to build the Epi-illumination modules, I'll demonstrate two practical Epi-illumination configurations of PUMA and show you some sample images. First, we'll look at PUMA as a biological Epi-fluorescence microscope for fluorescence. This setup uses the blue light illuminator with its 450 nanometer excitation filter, the 5 mm spacer, the 2 by 23 mm lower collector, and fitted with the LC Adjust collar module. This assembly was described in detail in the video on the LED illuminator. The PUMA light power supply will be used to drive it. This is described on the PUMA GitHub site. The illuminator is connected to the Epi-illumination port of the advanced filter block with the non-polarizing connector, composed of the Epi attachment and M3 adjustment ring modules. To minimize any back-reflected blue excitation light, we'll be using the Epi condenser light sink under the stage. For these tests, I'll be using the standard Optarc planachromat objectives, the same ones used for normal white light transillumination microscopy. Finally, we'll use this yellow 510 nanometer bandpass filter in the upper filter slot to block residual blue stimulating light that reflects up off the glass and specimen. Details of this filter are in the bill of materials on the PUMA GitHub site. The specimen I'll be using today is the fluorescence-stained section of plant tissue from the Optarc test slide set. This first set of images you are seeing are the whole field of view images using afocal eyepiece projection. These show various structures of a histological section of a flower bud. To keep the video short, I won't dwell very long on each image. You can use the YouTube pause facility to examine the images for longer if you wish. Note that the illumination is reasonably even across the whole field, with some drop-off to the periphery, exaggerated by the eyepiece camera projection used. Note the crisp, bright signal and dark background in the plant tissues. The spiky round objects are pollen grains, and we will see them in more detail soon. I'll now show you the same specimen imaged with direct chip projection to a C-mount camera using a x40 objective. Here are some examples of vascular coil structures seen at slightly different focal planes and with some images showing you the average of several focal planes. There is some background noise in these images, and that's because the camera used is not a dedicated low light level cooled CCD camera, but a generic CMOS camera used for bright field microscopy. These fluorescent test slides are deliberately made with thick sections, so you won't get the whole specimen in focus in a single plane. The specimen thickness was chosen so you can perform 3D deconvolution microscopy experiments, but I'll be discussing deconvolution microscopy with PUMA in another tutorial. For now, notice the dark background and good contrast rendered with the PUMA Epi-fluorescence system. The dark background is especially important when looking for very faint fluorescent signals, as shown here. Now I'll demonstrate PUMA as a reflected light microscope. I'll also show a comparison of some of the PUMA results to images of the same specimen taken with the same camera using this professional Olympus BH2 BHT-ML metallurgical Epi-illuminator microscope. This microscope uses Infinity Olympus MS Plan objectives and Olympus eyepieces, but PUMA will be using the standard Optarc finite tube length 160 mm planachromat objectives of the kind used for ordinary transillumination microscopy, as well as the standard Optarc eyepieces. The PUMA configuration uses the white light LED illuminator, and this time the illuminator is fitted to the Epi-illumination port with the polarizing connector. The polarizing analyzer is also used in the top filter slot. The specimen is the mounted silicon chip wafer fragment slide from the Optarc test slide set. This silicon chip fragment contains one or more copies of an integrated circuit die. Before we look at the silicon chip die, here is an example of reflected light epi-illumination for a circuit board from a CMOS camera at low magnification. Note how rotating the polarizer greatly improves the contrast by filtering out some of the back reflected light. Note also how some structure, such as the printed information on the components, can be greatly enhanced or even disappear, depending on the angle of polarization of the illuminating light compared to the angle of the analyzer filter. We will now examine the silicon chip die using Afocal eyepiece projection with both the Olympus BH2 metallurgical microscope and PUMA. The two microscopes have different magnification objectives apart from the ×10, so the comparison cannot be exact, but I include scale bars to aid comparison. For some images, you can see an indication of the polarization state in the top right corner for the PUMA images. I don't have a full polarization set for the BH2, so no polarization images are shown with this scope. In general, you can see that the Olympus MS plan objectives have superior planarity to the general-purpose Optarc plan objective. However, the even illumination across the field provided by the Olympus with its full color illuminator compares well to the even illumination provided by the PUMA Epi-Illuminator. I don't have an oil immersion ×100 objective for the Olympus scope, only this dry 100, which has a numerical aperture of 0.95, so it would be unfair to the BH2 to compare that to the PUMA oil immersion system. You can see this Olympus dry lens gives a rather misty image, but does show reasonable detail. The remaining images in this experiment are only taken with the PUMA scope. The comparison to Olympus ends here. We now move on to higher resolution imaging using direct chip projection with the C-mount camera. These images are taken with a ×40 dry Optarc objective. Now, I'm not an expert in microelectronics, so I won't pretend to know what I'm looking at in these pictures, but I'd be interested to know what you think the various components are. Please leave your views in the comments, and to assist this, I've overlaid grid reference lines at the sides so you can identify structures you wish to discuss. Note that with different states of crossed polarization, you see different parts of the circuit elements being emphasized. Also note these dark structures here. Even with this high magnification, we are not seeing what's going on in here. When I show you the oil immersion images shortly, the reason for that will become clear. So now we will look at the highest magnification and resolution possible with standard light microscopy using the ×100 Optarc oil immersion lens with a numerical aperture of 1.25 and using Leica immersion oil. As before, you can see the polarization status on the left, but now we also have an added benefit of a very fine depth of focus, so we can actually focus in on different layers of the chip, and thanks to diffraction, we can also partly see through opaque layers on top to structures on the lower layer. The layer depth is also indicated on the panel on the left. These images are from the large reservoir-like areas we saw at low power. I wonder if this is some kind of memory storage. And if so, what kind? Any microelectronics people watching this, please let me know in the comments. I'm amazed at the level of detail with which these prints have been made. If we look at this gap here, for example, you can see that the gap is just at the limit of our resolving ability, being about 200 nanometers or so, and therefore showing two things. One, we really are using the full numerical aperture resolving power of the objective, as I stated earlier, and two, the printing of these circuits is done with super resolution techniques, because even smaller gaps appear to be present beyond our ability to resolve with white light in this setup. Now we have depth information, we can see why those dark structures we saw with the ×40 lens didn't reveal much. Here we see some of those structures, and you can see that they consist of intricate structures at different depth planes. With the ×40 lens, these depth planes were not resolvable, they were superimposed on each other, and so the structure as a whole looked nondescript. With the ×100 oil objective, we can see the individual layers and make some sense of it, although I still don't know what this is, so perhaps someone can enlighten us in the comments. Before I move on to the next part of this video, I would ask that if you like these PUMA videos, please take a second to support the project by clicking on the big red subscribe button and give the video a thumbs up. If you have social media accounts, also please share these videos on them using the YouTube share button. Okay, now back to the rest of this video. These are the parts and the tools you'll need to build the PUMA Epi-Illuminator system. Details are given in the video description. As ever, the first steps after printing involve removing any support structures or stray plastic defects. Ensure any printed thread mechanisms are clear, and these may need to be scraped and finished with a wire brush to ensure they work as intended. Make sure any dust produced by these cleanup procedures is removed prior to fitting any optics. The advanced filter block, LED illuminator and lower collector were described in separate videos, so that instruction will not be repeated here. The Epi-black body and Epi-condenser light sinks, the Epi-condenser apertures and protective caps just need printing plus the optional application of an internal matte black coating, so no further instruction details are necessary for these parts. You'll notice that I have here a complete polarizing condenser module. This was described fully in the video on the polarizing condenser, so I won't repeat those details. The reason I have this module is that the polarizing attachment for Epi-illumination is just the polarizing condenser with this top element, the pole-to-baseplate component, simply swapped out and replaced with this Epi-pole component. Just ensure you grease this aspect before fitting it, as was shown in the video for the polarizing condenser. And here is the finished product. The plain Epi-illuminator connector is made by screwing the M3 adjustment ring component to the Epi attachment component. You prepare the M3 adjustment ring by inserting the M3 nuts into their recesses here, and make these M3 adjustment screws exactly as was shown in the videos on the polarizing condenser and curler illumination. So this instruction will not be repeated here. When assembled, either of these connectors simply screws into the Epi-illumination port of the advanced filter block, as shown. The Epi-illumination port is the port that faces back towards the focus gears when the optical tube is inserted into the focus plate. To complete the assembly, attach the LED lamp and lower collector with the LC adjust collar in place to the M3 adjustment ring component as shown. You can vary the angle of the illuminator to get the best even illumination, similar to the adjustment shown in the video on the polarizing condenser. If not using the augmented reality projector, you screw the Epi-black body into the other side of the filter block. This expanded portion of the Epi black body allows you to get greater stability and to compensate for any uneven stress placed on the optical tube by the weight of the Epi-illuminator by fixing it in place with the AR clip, clip lock and stay mechanism, which is also used to support the augmented reality projector. To use this stabilizer, first insert a 12 mm long M4 screw into the front M4 nut of the focus platform, but do not use a washer. You should tighten this screw, we won't need to adjust it. Now prepare the stay thumb wheel by inserting an M4 nut into the recess for it. Prepare the clip lock module by inserting an M3 nut into this recess similar to the way you did for the illuminator adjustment rings. Make the M3 thumb screw as previously described for the illuminator adjustment thumb screws. Now thread the stay thumb wheel over the M4 screw in the focus plate. Put the clip module over the expanded part of the Epi black body with the articulation facing off to one side. Then rotate the clip and stay thumb wheel till the opening of the stay thumb wheel is level with the articulation of the clip. Now you can clip the articulation into the stay thumb wheel. Rotate the stay thumb wheel a further quarter turn to ensure the articulation won't come out. You can now slide the clip lock over the clip from the front, ensuring the open side of the clip lock faces the lugs on the clip. And lock the system in place by means of the thumb screw. You can adjust the tilt of the optical tube backwards or forwards slightly by adjusting the stay thumb wheel. Remember to release this clip lock mechanism whenever you need to remove the optical tube, for example to change objectives. Your PUMA Epi-illuminator is now complete and ready to use. Other forms of Epi-illumination are possible with this apparatus, in addition to the examples shown in this video, such as backscatter dark field and oblique Epi-illumination. Details of the various types of Epi-illumination that can be achieved and experiments using Epi-illumination will be the subject of separate tutorials. Please remember to subscribe, like, comment and share this video to support the PUMA open source microscopy project. Thanks for watching.